Hi everybody, this is Eduardo Suarez. In this second part of the video, we're going to continue with the TicTacToe KAREL program, and I'm going to show you how to implement the MiniMax algorithm. We're going to start by renaming the work cell that we did in the previous video, and we're going to call it TicTacToe MiniMax. And the other thing that we're going to do, we're going to select files, we're going to right click, we're going to go to set default folder, and we're going to select the folder for the work cell and press OK. We're going to review for a moment what the MiniMax algorithm does. We're going to start from a predetermined condition as shown here, and we're going to have two players, the maximizer and the minimizer, and both of them have opposite interest. The maximizer tries to maximize the score, while the minimizer tries to minimize the score. We're going to consider that the score is going to be +1 if the maximizer wins, and it's going to be -1 if the minimizer wins. If there is a draw or the score is undetermined based on the position of the game, we're going to set the score to 0. Based on this predetermined condition, now it's the turn of the maximizer to move, and we're going to represent the move with the branches as shown here. On the second level, that is depth equal to 2, from left to right, here we have a win for the maximizer, and the score is going to be +1, and on these two other positions, the score is undetermined, so we need to go one level down. On the second level, when depth is equal to 2, is the turn of the minimizer to play. Again, we're going to represent the possible moves with branches, as shown here. We're going to go one level down. Now, when depth is equal to 1, from left to right, the three first positions, the score is undetermined, and for the last position, we have a win for the minimizer, so the score is going to be -1. Still, we need to go one more level down to determine the score for these three positions. When depth is equal to 1, is the turn of the maximizer to play, and there is only one possible position that the maximizer can play. So when we go to one level down for depth equal to 0, we can determine the score. From left to right, we're going to have a win for the maximizer, so the score is going to be +1, and on the other two positions, we have a draw, so the score is going to be equal to 0. Now we need to start doing the evaluation in reverse order. For depth equal to 1, we're going to transfer the score from the lower level, so we're going to have +1 on this position, we're going to have 0 on this position, 0 on this position, and we know already that we have a -1 for the last position. Now on depth equal to 2, since it's the turn of the minimizer to move, the minimizer is going to select the lowest possible score between all the score that we have from the lower level. So in this case, the move that it's going to select is going to be 0, and on the other case, the move that it's going to select is going to be the one that leads to -1. So finally, now is the turn of the maximizer to move. That's going to be for depth equal to 3. The maximizer again is going to select the move that leads to the highest score possible, and from these three possible moves, the maximizer is going to select +1. So it's going to discard all these two other moves. And that is how the MiniMax algorithm works. One more thing, in this example, we were able to go to the end of the game, where we were able to determine the score of all the possible moves. In practice, this is not always possible, because doing that would require a very high volume of calculation. In that case, you will have to limit the number of levels that you want to extend further down in the calculation. And you need to figure out how you're going to determine the static evaluation for the score. And by static evaluation, it means to estimate the score without making any other moves. We're going to go back to the work cell, and before we start working on the MiniMax algorithm, we're going to create a new KAREL program that we're going to need later. We're going to go to Files, New File, KAREL Source. We're going to copy this program. And we're going to name it random number. What this program does is going to generate a random number from 1 to 9 that we're going to use it for placing the first position for the robot. If you want to get more information about how this program works, you can look at my previous video, KAREL Programming Guess a Number. So we're going to build it, and we're going to see how this one works. We're going to open the Teach pendant. We're going to press Select. We're going to look for random number, and we're going to execute it. We're going to select data. We're going to select type, KAREL variables, and you're going to see the random number that was generated was number 6. And this number is based on a seed and all the logic that is in here. One more thing that you can notice is that when we declare the variable seed, it has an instruction that says in CMOS. That means that this variable is going to be saved retentively on the memory of the robot controller. So the next time we cycle power the controller, we are not losing the value of the seed. If we execute the program again, let's run it again. And we're going to go back to the variable. You're going to see that we have now a new random number. Now we're going to open the TicTacToe program. We're going to select everything, we're going to copy, and we're going to create a new version. We're going to paste it in here. We're going to call it version 2. And we're going to start making the changes that we need for the MiniMax algorithm. We're going to create a new routine. We're going to go over here, and we're going to paste this routine in here. And what this routine is doing, this is going to be a function routine. We're going to pass a board, and we're going to pass a mark that's going to be a string, and it's going to return a boolean. Basically, with this routine, we want to know who won, if that was a robot or the player, and I'll show you in a moment how this is used. We're going to go to the robot move routine. We're going to select it, and we're going to delete it, and we're going to replace it with a new version. So in this new version, in this routine, we're going to pass the board, we're going to pass the first move, that's going to be a boolean, and we're going to pass a random number that's going to be an integer, and this is going to be a procedure routine. It's not going to return anything. We're going to define our variables, and over here we're going to initialize the variables. We're going to have robot, that's going to be a string of 1 character. We're going to have the best score, that's going to be the worst possible number that we can have for the robot move. In this case, we're going to select a number that's going to be -1000, and we're going to select the best move, that's going to be 0. We're going to define the dimension, it's going to be the length of the array for the board, and we're going to select a depth that we can put a number like 6 for now, and this is going to be how deep we're going to go in the algorithm of searching down. Over here, we're going to make a decision. If we are making the first move for the robot, the best score is going to be 0, and the best move is going to be a random number. Otherwise, we're going to start searching all the possible moves that we can do with the robot for that particular position. So we're going to go from 1 to the dimension of the board. We're going to look for an empty position on the board. And in that case, we're going to set the board position equal to robot. And we're going to call the MiniMax routine that we haven't defined yet. And we're going to pass the board, the depth, and a boolean that's going to be false. And I'm going to explain you in a moment how this one works, but basically what we're saying here, that the next move is going to be for the player. Once we get the score, coming back from the MiniMax routine, this is going to be a function routine that's going to return an integer, and the integer is going to be the score for that particular move. We're going to clear the move from the board. We're going to determine if the score is bigger than the best score, that we define the best score as minus 1000. And in this case, we're going to update the best score with the value of the score, and the best move with the value of the move that we have over here on the search algorithm. And we're going to keep repeating the for loop until we go to the end of the board. So we're going to be searching for every empty position that we have on the board. So basically what we were doing with the routine, when it's the turn of the maximizer to play, we're going to look for every empty position and we're going to do that move. As in this scenario, we're going to play over here, we're going to play over here, and we're going to play over here, and we're going to determine the best score using the MiniMax algorithm. Now we need to create the MiniMax routine. We're going to go over here after the insert later routine, and we're going to copy this logic. So this is going to be a function routine. We're going to pass the board, we're going to pass the depth, we're going to pass a boolean that is maximizing, and it's going to return an integer that's going to be the score. We want to define our variables. It's going to be the robot is going to be a string of 1, player also is going to be a string of 1. We're going to have the score, the best score, the integer that we're going to use for the for loop, and we're going to define the dimension of the board. We're going to initialize our variables, and the first thing that we're going to do over here, we're going to call the routine check which mark 1 that we created recently. We're going to pass the board, and we're going to pass the mark that in our case is going to be the robot, and we're going to check if the robot won. In that case, we're going to return the score that's going to be +1. If the robot didn't win, we're going to check if the player won. So we're going to call the same routine again. We're going to pass the board, and we're going to pass the mark as a player. And if the player won, we're going to return a score that's going to be -1. We're going to keep checking again. If we don't have a win for the robot and we don't have a win for the player, we're going to check for draw. In that case, the only argument that we need to pass to the routine is the board. In the routine, we're going to check for an empty position, and if we don't have an empty position on the board, and we don't have a win for the robot or the player, that means that there is a draw, and in that case, we're going to return 0 for the score. And lastly, we're going to check for the depth equal to 0, and we didn't have any win and we didn't have any draw, and in that case, we're going to return also the score equal to 0. If we don't have any of this condition, we're going to go over here and we're going to start executing the MiniMax algorithm. The first decision that we're going to make is going to be the Boolean that we're passing as a parameter over here, and this Boolean is going to represent if the maximizer is player or the minimizer is player. If the Boolean is true, that means that the maximizer is playing, and we're going to execute this part of the program. If the Boolean is equal to false, that means that it's a turn of the player to move, and we're going to execute this part of the program over here. Again, we're going to define the best score as -1000, and we're going to search every possible move that we can do with the robot on the board. So it's going to be very similar to what we did before for the robot move. We're going to search the board for an empty position. In that case, we're going to place the robot on that position, and we're going to call the MiniMax routine again. What we're doing here, we're making a recursive call to the same routine, MiniMax. In this case, we're going to pass the board with a new position for the robot. Depth is going to be the depth -1. We're going to level down, and we're going to pass as a Boolean false. That means that the next move is going to be for the player. When we return the score, we're going to put the position back to empty, and we're going to determine if the score is greater than the best score that was -1000, and in this case we're going to update the best score with the score. At the end of the for loop, we're going to return the best score. And we're doing exactly the same over here if that's the case for the player to move, but it's going to be a little different. We're going to have the best score as +1000. When we call the MiniMax routine as a Boolean, we're going to pass through. That means that the next move is going to be for the robot, and instead of looking for the greatest possible number, we're looking for the lowest possible number. So in that case, if the score is lower than the best score, we're going to update the best score equal to score, and at the end of this, we're going to return again the best score. That's going to be the value that we're returning over here. If we look at our example again, we're going to play the robot first, and then we're going to call the MiniMax algorithm with all the possible moves that we can do for the robot. And then we're going to check for a win if the robot wins, or if the player wins, or there was a draw. If that's not the case, we're going to go one level down, and it's going to be the turn for the player to move. So we're going to be calling over here the MiniMax algorithm. We're going to go to this position, and we're going to call again the MiniMax algorithm. One level down, we're going to check again if there was a win or a draw. We found in here a win for the player, but this one is still undetermined. So we're calling again the MiniMax algorithm. We're going one level down, and this time we're going to pass through for the robot to move until we reach the lowest level possible in our search, where we have a win of a draw. And every time we're going to pass in the score one level up. One thing that you need to know is that every time you're calling the routine recursively, you are creating a stack for the previous call of the routine, and it's taking memory on the robot controller. So there is a moment that you're going to run out of memory on the controller. If you want to know how much memory the stack is taking, you can get that information from the KAREL reference manual. Now we're going to make a few more changes. We're going to go to the variable declaration section of the program, and we're going to define two new variables. It's going to be random number. This is going to be from the random number program. It's going to be an integer. And we're going to create another variable that's going to be first move. That's going to be a boolean. We're going to go to the executed section of the program. We're going to make a few changes. Over here, we're going to put a delay of 1 second. Then we're going to call the program random number. On the initialize variables, we're going to initialize first move equal to true. We're going to take this line of the program, we're going to delete it, and we're going to replace it with this condition over here. We're going to check if the first move is equal to true. In that case, we're going to call the robot move routine, and we're going to pass the board, the first move, and the random number, and we're going to set the first move equal to false. Otherwise, we're just calling the robot move routine. We're going to set the program, and we're going to build it. Before we run this program, we're going to make one more change. We're going to keep track of how many moves we're doing with the MiniMax algorithm. We're going to go to the MiniMax routine. We're going to declare new variables, integer moves, real moves, a flag, and status. We're going to insert these lines over here. What this instruction is doing, we're going to read the register number 1. It's going to read either an integer value or a real value. In our case, we're going to read the integer value. That's going to be the number of moves. And we're going to increment the number of moves by 1. And then we're going to write back to the register 1 using the set integer register, and we're going to pass the integer number moves. We're going to go to the robot move routine. We're going to declare two new variables. Over here, we're going to initialize register 1 to 0. We're going to go to this line of the program, and we're going to add two new lines. It's going to be moves equal to 1, and we're going to write the number of moves that's going to be 1 to register 1. We're going to save the program, and we're going to build it. We're going to make one last change. We're going to go to the MiniMax routine. We're going to take this variable over here, versus score. We're going to delete it, and we're going to replace it with maximum evaluation and minimum evaluation. And over here, we're going to change the variable. With this, we're done with the TicTacToe program, and we can close it. We're going to open the Start Game. We're going to select it. We're going to create a new program. We're going to copy this Start Game in here, and we're going to make a new version. We're going to save it, and we're going to build it. Now we're ready to run the program. We're going to open the teach pendant. We're going to split the screens. Over here, we're going to select data, and we're going to select register number 1. And over here, we're going to select the start game program with a new version that we have created. We're going to select it, and we're going to run it. We're going to press S4, and the robot moved. In this case, is random move, and use the random number 5. You can see in register number 1 the number of moves it took. It was only 1. Now it's the turn of the player to move. We're going to select position number 1. Now the robot moved again and use position number 2. You can see on register number 1 the number of moves that the MiniMax algorithm took to figure out the best possible move. Now it's the turn of the player to move. We're going to block the robot with position 8. The robot played again and use position number 4. You can see again on register number 1 that now the number of moves that the MiniMax algorithm used was less than for the position before, because now we have less position available. We're going to block again the robot with position 6. And now it's the turn of the player to move. It took this time only 15 moves. And we're going to block the robot with position 7. And in this case, there was a draw. We can start the game again. We're going to press F4 again. It took the same position, but remember this is a random position. So randomly took 5 again. We're going to play position number 2. We're going to block the robot with position number 9. And we're going to block the robot with position number 7. And in this case, the robot won. Now we're going to press F5 to finish the game. In this example, we set the depth for the recursive calls for the MiniMax routine to 6. We can limit that number, and we can see how the MiniMax algorithm responds. We're going to go back to the TicTacToe game. We're going to scroll down to the robot mode routine, and we're going to change the depth from 6 to a number, for example, 4. We're going to save it, and we're going to build it. We're going to go back to the teach pendant. We're going to select the program again, and we're going to run it one more time. We're going to press S4. The robot this time use position number 2. It took only 1 move. We're going to play with position number 5. You can see this time it took less than before to check all the possible moves to get the best possible position, and it used position number 1. We're going to block the robot position number 3. Now it chooses position number 7. So position number 7 is going to block us. So I need to block the robot with position number 4. And now we're going to select position number 9. And there was a draw. You can see by reducing the depth of the recursive calls, we are reducing the number of estimates that the MiniMax algorithm can do. As a result, the best possible position is going to be less accurate. In conclusion, I show you here how the MiniMax algorithm was implemented for the TicTacToe game. Using the MiniMax algorithm, the robot is able to play by itself, and either it's going to win or it's going to be a draw. Also, we saw that the result of the MiniMax algorithm is very dependent on the depth of the recursive calls, as we start incrementing the depth, the number of moves is going to search to get the best possible move, also increases, and the result is going to be more accurate. There is a way that we can optimize the MiniMax algorithm to reduce the number of moves during the search, and that is using the alpha-beta pruning. And we're going to leave the alpha-beta pruning implementation for the next video. That is all for now. I'm going to leave the link to the work cell on the description below, and thank you for watching.